Hi class, welcome to an example problem for Unit 8.3. In this problem, we're going to talk a little bit about different ways that we can have impending motion. So what we have here, this is problem 8.53 in the 13th edition of the textbook. We have this wheel, this cylinder, that has this vertical force being applied called P, and I know there's some glare right there, so it's a little hard to see. This wheel has a diameter or a radius of 1.5 feet, and this wheel is tied by a cable to a block C that's 3 feet tall, 1.5 feet wide. We're told that the coefficient of friction between the wheel and the ground is 0.2, and between the block and the ground is 0.3, and we're told that block A weighs 20 pounds and C weighs 30 pounds. And what we're asked to find in the first part is the smallest vertical force P that can be applied to the wheel, which will cause impending motion. And by my count, there are 3 different ways that there can be impending motion in this problem. First is the wheel slips. Second is that the block slips. And the third is that the block tips. So one of those 3 is going to be the way that we end up having impending motion. So this is one of those kind of problems where you're going to have to make some assumptions about what's going to occur first and kind of solve it out that way. And then in the second part of this problem, something that I added is assuming that tipping is not the first mode of impending motion, how much taller should the block and disc be to ensure that we will have tipping happen first? So hopefully that makes some sense. This is a little bit tricky, but if we just follow our same basic fundamentals of drawing good free body diagrams and using our basic equations of static equilibrium, then we should be golden. So I'm going to actually draw both free body diagrams here to start. So we have this wheel, and this wheel has a force P applied. It has a tension. It has a weight. It has a normal force. And it has a friction force. And then we have the block, which similarly has a weight, a normal force, a tension, which is the same tension as what's felt by the wheel, and a friction force. So I'm going to make an assumption, and my assumption is that the wheel is going to slip first. So assuming that then I can say that friction force FB is going to be NB times 0.2. So that's my first assumption. So let me try to get some, and we're just going to start throwing out my equation. So let's start with the easiest one, is sum of forces in X, which tells me that I got positive tension minus friction force. And if I sub in my first relationship there, I can get that tension is going to equal, also going to equal NB times 0.2. Now let's look at my sum of my forces in Y. And that's, I'm going to have a minus P, a minus W, and a plus NB. And so I can rearrange that and say that NB equals P plus 20, because that is the weight of the disc. And now I'm going to do my moment what I need to try to find is, I need to find P. So I need to find an equation where I can get P. So I'm going to take the moment. Let's do the moment about point B. About point B. So the sum of the moments about point B. Point B is nice. It cancels out really everything except for P and T. Sum of the moments about point B. 0, have the radius P, so I get P times 1.5. And then tension is going to cause a negative moment, so minus tension. But its moment arm is actually the diameter, because I'm doing it at D, not the center, the diameter. So I get times 3. And so I can substitute in, I know, so I'm going to sub in 2 and 3 to get that P 0 equals P times 1.5 minus tension, which is really just, I know tension is just NB times 0.2, and NB is P plus 20. So P plus 20 times 0.2 times 3. And if I do some rearranging and some math, I will wind up finding that P equals 13.3 pounds. So if the wheel slips first, then P will be 13.33 pounds. And by extension, I know tension is going to be 1/2 of that, so I'm just going to write out the number. That tension is 6.66, because I'm going to be using that over here. So now what we need to do is check if these assumptions are right, then these should hopefully not slip first. So I know that if the friction force at D, the max that it can be, is going to be, well, before I get to that, I'll do that now. So the friction force at D max is just going to be ND times 0.3. That's the maximum it can be. So whatever this value ends up being, I can't exceed it. Now, if I do my sum of forces in Y, then I get that ND, I get ND minus WC, and so I know ND is just going to equal 30. If I plug that in here, then it's clear that the maximum force is 9. So if when I plug in T up here for this free body diagram, if the resulting friction force is greater than 9, then I'm in trouble. Well, I'm not in trouble. That just means that this will slip before the wheel slips. So let's look at that. I can get that just by doing a simple sum of forces in X. Sum of forces in X equals 0. That just tells me that friction force D minus T must equal 0. Well, I know T is 6.66, so therefore friction force D is equal to 6.66. So it's just equal to whatever that tension is. In this case, that tension is half of P. So that's less than 9, so it's not going to slip first. So now we just need to check our last potential way that we could have impending motion, which is if the box tips. Now with tipping, the idea is that my moments still have to balance, right? And so as this force increases, that's going to cause, in the case of this box, it's going to cause a positive moment. And the only way to balance that is by moving my normal force more and more to the left to cause a counteracting negative moment about the center of gravity. And so you can kind of think of it as, okay, ND is no longer acting right at the center of gravity, or right under the center of gravity. It's scooching more and more to the left until eventually it's going to be acting right at the edge of the box. All the way that box is going to be really just put right on the corner of the box. And that's as big of a force that can be sustained by the box without it causing the tip. Because in order to, if that was any bigger, the moment would, or the normal force would have to be off of the object, at which point obviously it can't actually exert any force. But it would have to be out there to keep the moments balanced. So if it's any more than that, it is going to tip. The moments can no longer remain balanced. So that is sort of what we're looking for, is making sure that this marker, ND, that distance, the moment arm distance, can't be any more than half the width. So 0.75 is the magic number to keep an eye on. So let's do our sum of the moments. And I'm going to do it about point D here at the bottom center of the box, just so I can ignore the friction force and the weight. So about point D is 0, which is going to be have positive tension times the height of the box, which is 3, minus ND times some distance that we are solving for. So we already know tension is equal to 6.66. So that gets us that, and we know that ND is equal to 30. So we get, we get that distance is going to equal to 6.66 times 3 divided by 30. And that ends up getting us that the distance is 0.666 feet. So because the distance is less than 0.75, which would stick it at the very corner of the box, we do not experience tipping. So the wheel does indeed slip first, and the minimum force that can be applied is 13.3 pounds. So hopefully that kind of made some sense. Now for this part B, now that we have all this figured out, it's actually very simple. All we need to do is go back to this equation, and instead of the distance being unknown and the height being known, we'll have the distance known and the height will be unknown. So it's sort of a reversal of how we think about it. So I'm going to erase this side just so I have space to do that. So I'm going to start with the exact same sum of moments equation. And so now, right, we're just trying to find how much taller would the box need to be to make sure that tipping is the first way that we have impending motion. So sum of the moments about point D equals 0. That equals the tension times the height, and then minus ND times 0.75. So now we're assuming it is right on the corner where that's acting. And so with some relatively simple rearranging, we get the height equals, right, ND is still 30, so 30 times 0.75 divided by the tension, which is just 6.66. And that gets us at the height. It would have to be 3.3784 feet for tipping to be the first the first way that this system would start moving. So not that much taller. We're actually pretty close to it. So hopefully that makes some sense. Hopefully the whole tip versus slip idea makes good sense now. I know it's a little bit confusing, but intuitively it makes some sense. You can kind of visualize, if I have a tall dresser and I push, it's going to start tipping around. You can kind of imagine that more and more the weight's shifted to the far end. And obviously it kind of makes sense that if you're pushing a tall dresser versus like a short table, the tall dresser could tip over, the table probably won't, especially if it has a wider base, right? So that's kind of why the wider the base of something is, the more stable it is. And kind of why, if you can only lean forward so much before, and in fact, yeah, maybe that's a good way to do it, right? If you lean forward, you can feel that more and more of your weight shifts to your toes. And eventually there's a point where your toes just can't provide that restoring moment to keep you from leaning forward. So hopefully that makes some sense and clears some things up. If you have any questions, as always, let me know. I'm happy to chat anytime. So thank you for watching.